Welcome back to Statistics. You'll recall from our discussion of confidence intervals that there's always some uncertainty attached to the question of whether the confidence interval you just calculated and you're looking at right now, whether that confidence interval truly contains the population mean. That's why we label confidence intervals with a confidence level. A 95% confidence interval, for instance, is one calculated with a margin of error so that 95% of all x bars will contain the true mean within the margin of error. But the corollary is that 5% of x bars will not contain the true mean in the confidence interval. And the uncertainty that you have is you don't know whether your confidence interval is one of the 95% that are good or one of the 5% that are incorrect. But you have 95% confidence precisely because 95% of all 95% confidence intervals are good. They do contain the population mean. Well, there's a similar kind of uncertainty that attaches to the decisions we come to in significance testing. You may be performing a significance test of a null hypothesis versus, say, a one sided or two sided alternative. And you may go get your sample data, compute a sample mean, do all the computations, the test statistic, the p value, and so on. And you may, for instance, arrive at a decision to reject the null hypothesis. That doesn't necessarily mean that the null hypothesis was false. It just means that the null hypothesis wasn't consistent with the sample data you collected. If you incorrectly reject the null hypothesis, and assuming all your computations and so on were correct, the reason for the mistake would have to come down to your sample data, right? Your sample data would have to have been unrepresentative, way out in the tails of the sampling distribution. And that's what would cause you to falsely reject the null hypothesis. There's a second kind of error that you could make as well, right? You could fail to reject the null hypothesis even though the null hypothesis was in fact false. So that's a second kind of error that you could make. And again, that would be an error not deriving from some mistake in your calculations, but rather based on the sample data, right? It's just possible that you could have got sample data that was so unrepresentative that it caused you to make a mistake in the decision to reject or fail to reject. So we'd like to be able to quantify the probabilities of these kinds of errors in significance testing. It's very much like the kinds of errors that can happen in a criminal trial, for instance, where we've already discussed the analogy between the presumption of innocence and the null hypothesis in a significance test. It's possible that you could reject the presumption of innocence in a criminal trial incorrectly. That is, you could find the defendant guilty even though he or she was in fact not guilty. The other kind of error you could make would be in finding the defendant not guilty when in fact he or she was guilty. So, in contrast to the situation with confidence intervals, there's really two kinds of errors that can be made in significance testing. And we want to quantify and discuss the relationships between those two kinds of errors in this short video. So let's take a look. type 1 and type 2 errors. That's the terminology used to refer to these kinds of errors in tests of significance. And let's begin by talking about type 1 errors. Type 1 errors occur when we falsely reject the null hypothesis. That is, the null hypothesis is true, but carrying out the significance test completely correctly results in a rejection of the null hypothesis. Let's think about this in the context of a one-sided test of the null hypothesis that mu equals some value, which I'm calling mu0 here, versus the alternative that mu is greater than that null value. And let's do the test at some significance level alpha. Suppose the null hypothesis were actually true. Of course, you wouldn't know this in doing the test. If you knew that the null hypothesis were actually true, there would be no need to do a significance test in the first place, right? But let's just suppose, for the sake of argument, that the null hypothesis is actually true. Well, here's kind of a picture of that situation. I'm drawing the sampling distribution of x bar, and since the null hypothesis is true, we're assuming, the mean of that is actually our null value mu0. We're doing the test at significance level alpha, and it's a right tail test, so I've shaded in the rejection region there in yellow. And the area under the curve is, of course, our significance level. You could think 5% or, whatever. What is the probability that we would actually reject the null hypothesis even though it's true? Well, that depends completely on the x bar value that we get from our sample data. If we observe an x bar value that's not in the rejection region, we're going to fail to reject the null hypothesis. And that would be a correct decision, right? Because again, we're assuming the null hypothesis is true. This again would be an x bar that would cause us to fail to reject the null, and that would be a correct decision, assuming the null is true. This, on the other hand, would be an x bar that falls into the rejection region. Its p-value would be less than alpha. However you want to look at it, this value of x bar would cause us to reject the null hypothesis. And that would be an incorrect decision, right? Because the null is actually true. But this could occur. That x bar value is totally possible if the null hypothesis is true. In fact, we know the probability of all such x bar values. It's precisely the area that's shaded under that curve, right? So the probability that we would reject the null hypothesis when it's true is precisely our significance level alpha. So that's another way to think about the significance level of a significance test. We say that a type 1 error occurs when a test rejects the null hypothesis H0 when the null hypothesis is in fact true. And what we've just seen is that if the null hypothesis is true and we carry out a significance test with significance level alpha, then the probability of making a type 1 error is precisely alpha. And so if you wanted to reduce the probability of making a type 1 error, that is, of falsely rejecting the null hypothesis, you would reduce the significance level alpha. You would take it from 5%, say, to 1%, or if that's still too much, you might take it to 0.1%, and so on. Let's see how this works in the context of missile defense systems. Missile defense systems such as THAAD stands for Terminal High Altitude Area Defense, have components that attempt to provide early warning of a missile attack by an adversary. In a scenario like this, there are two competing hypotheses. The first would be that no attack exists. No attack is underway. All is normal. The second would, of course, be that an attack has been launched. Now, given what we've said about null and alternative hypotheses, which of these do you think is more appropriate to label as the null hypothesis for a significance test? I think if you think about it a minute, you'll agree that the null hypothesis should be that no attack exists. That's the normal state of affairs, sort of the hypothesis of no change, no difference, so on. So the alternative would be that an attack has been launched. Now, given these two hypotheses, what would a type 1 error be in this situation? Well, remember, a type 1 error is the error of falsely rejecting the null hypothesis. That is, the null hypothesis is true, and yet you reject it. And so in this situation, that would mean that it's true that no attack exists, and yet your belief is that an attack has been launched. That would be a type 1 error. You could describe this as a false alarm, sort of in layman's terms, right? No attack is really underway, but you're raising the alarm that an attack has been launched. That would be a type 1 error. What would the consequences of a type 1 error be in this sort of situation? Well, they could be pretty severe, right? No attack is actually underway, and yet you raise the alarm. An attack has been launched. What could happen? Well, very likely you would launch a counterattack. Maybe that involves launching your own ballistic missiles at your adversary. Think about how that looks from the other side, from the adversary's point of view. They haven't launched an attack, and yet, all of a sudden, here come missiles from the other side. The consequences of a type 1 error in this situation are pretty serious. You may have just started a war by mistake. If you wanted to reduce the probability of making that kind of error, that certainly seems like a desirable thing, you would do what? You would reduce the significance level of your test. If you are operating at an alpha equal 5% level, you might want to take it down to alpha equal 1%, or maybe even alpha equal 0.1%. That would reduce the probability of a type 1 error. And that in this situation, that would mean reducing the probability of sort of accidentally launching a thermonuclear war. What we're going to see, though, is that there are costs to that. By reducing the probability of making a type 1 error, you inevitably increase the probability of making what we call a type 2 error. So what's a type 2 error? A type 2 error is falsely failing to reject the null hypothesis. That is, the null hypothesis is actually false, and yet you fail to reject it. That's called a type 2 error. The probability of making a type 2 error is more difficult to determine than the probability of making a type 1 error. And that's for a simple reason. If the null hypothesis is false, that means that the alternative is true, or some case in the alternative, right? For instance, for a right-tailed alternative that mu is bigger than the null value, there are many possibilities for the true value of mu. And you can't really compute the probability of a type 2 error until you know which of those possibilities is actually true. So this makes computing the probability of a type 2 error more difficult. But still, there's a relationship between the probabilities of type 1 and type 2 errors that we can see pretty easily. So consider a significance test of the null hypothesis that mu equals mu 0 versus the alternative, the right-tailed alternative, that mu is greater than mu 0. Suppose that the alternative is actually true, and that in particular the true mean is equal to some value mu1, which is greater than mu0. So I'm drawing a little picture of that situation here. What you're seeing are the sampling distributions of x bar. The left-hand graph shows what the sampling distribution would be if the null hypothesis were true, right? And the mean were truly mu0. But we know that's not the case. We know that the true value of mu is mu1, and I'm showing that in the right-hand bell curve there. The left-hand bell curve is nevertheless necessary because you'll remember that we do a significance test under the assumption that the null hypothesis is true. And that yellow region you see highlighted in the left-hand curve is precisely the rejection region for the significance test. The area in the shaded region is our significance level alpha. We also know now that that's the probability of a type 1 error. And let's just assume, for sake of definiteness, that that's 5%. So we're doing a 5% significance test here. In this situation, when would a type 2 error occur? Well, it would occur when we fail to reject the null hypothesis, right? Because remember, mu1 is actually the true value. And so to be correct, we would need to reject the null hypothesis. If we fail to do that, we're making a type 2 error. When would we fail to reject? It would be when our x bar value is to the left of that shaded region. So what's the probability that we would fail to reject? It would be the probability of all x bars that are to the left of the shaded region, but the probability under the right-hand curve, right? Because that's actually the true curve. So it's the area of the red shaded region. That area is sometimes called beta, and it's the probability of a type 2 error, and in this case, it turns out to be 3%. Okay, so what would happen if we decreased the probability of a type 1 error, as we were discussing before? What would that do to the probability of a type 2 error? Well, to decrease the probability of a type 1 error, we need to decrease our alpha value, right? That means making that yellow shaded area smaller, moving its boundary to the right, in other words. What will that do to the red shaded area, which is the probability of a type 2 error? Well, it'll increase it, as you can see right here. By decreasing the probability of a type 1 error from 5% to 3%, it turned out we increased the probability of a type 2 error from 3% to 6%. And that's generally true. Decreasing the probability of a type 1 error increases the probability of a type 2 error, and vice versa. In other words, probabilities of type 1 and type 2 errors change in opposite directions. Increasing one decreases the other. Let's see how this plays out in our missile defense example. Again, we have our null hypothesis that no attack is imminent, no attack is underway, versus the alternative that an attack has been launched. So what's a type 2 error here, and what would be its consequences? Well, a type 2 error is failing to reject the null hypothesis when in fact it's false, right? So since we failed to reject H0, we would believe that no attack exists, but that would be false. An attack would actually be underway. The consequences of that, I think you can see, are pretty serious as well. We're essentially defenseless in the face of an attack. So what we've seen here is that the consequences of both a type 1 error and a type 2 error are fairly stark in this missile defense example. But on the other hand, trying to decrease the probability of one will inevitably increase the probability of the other. So, this is why when the consequences of making an error in a significance test are high, it can put the decision maker in a difficult position, right? And that's something to think about when you're thinking about decisions of any sort, but especially decisions of great consequence. I don't want to suggest that there's no way out of this dilemma. There are things that you can do to try to simultaneously make the probabilities of type 1 and type 2 errors small. You can also decide that, for instance, in other situations, not missile defense, but in some situations, you may decide that it's okay to live with a relatively large probability of one kind of error if, as a result, you can push the probability of the other kind of error very small. So, all these kind of options are available, and we actually discuss those in further courses. If you're interested, I would urge you to consider taking our Math 222 statistical methods, where we talk more about this issue among many others. But in the meantime, just wanted to give you a quick idea about some of the error analysis for significance tests. We will be back at you soon with more information on inferential statistics, and in the meantime, take care.